Hi there, welcome back to the formulaic approach. Now let us talk about refraction of light. Yesterday we talked about reflection. Today we are going to talk about refraction of light. And I have seen the comments that on the questions you asked me to review, I'm going to review those questions. It's just I'm having to shoot numerous videos at the same time. That's why I've not attended to them. Hopefully by tomorrow evening, and I only shoot at evenings after my work. So that's why I've not attended to the question. All right, so, but basically I'll make another video where I'll be treating questions only. Okay, and I'll treat some of those questions I asked. And thank you once again for keeping up. So let's talk about refraction of light waves. So I mentioned in the beginning yesterday that there are three different ways in which light can change its direction. We have reflection, which is just the bounce off of light, for example, or any wave, off of a surface, thereby resulting in a change in its direction, okay? Or a change in its direction. So for example, it was going in one way before, once it strikes an object, it will move in another direction. We call that reflection. Now, another way by which it can change its direction is refraction. Is what? Refraction. All right, let me show you what refraction is. Now, refraction we define as the change in the direction of wave. So in this context, I'm going to use light waves, the change in direction of light waves as its now it's not just the direction that changes, okay? The change in direction of light waves, the speed, so the change in direction of light wave, its speed also changes. The change in direction of light wave, speed, and the wavelength also changes. And wavelength of light as it moves from one medium, as it moves between media of different optical densities. I want to use the best language, okay? As it moves between media, that is between two or more mediums. So between media is the plural of medium. Between media of different optical densities. Now, what does optical densities mean? It means the level of compactness of the object, the level of permeability of the object to light, how much it can allow light to pass through. Okay, that's the optical density. So what that means is that water, for example, will be optically dense than air. Okay, glass also will be optically dense than air because it's more compact than air. All right. So that is what the change in the direction and speed and wavelength of light as it moves from one medium to another, provided they have the media have what? Different optical densities. Does that make sense? Now what that means is this, that the light will change its path of motion when it crosses from one medium to another. I'll repeat that. That is, if light is going from one medium to the other, it's going to change its course of motion. So what that means is this. If light is coming at a particular angle, this ray will be called the incident ray. We treated that yesterday, right? By the time it crosses the interface, this line I drew here is not solid. It's not a solid surface. It's like the interface between, let's say, air, for example, and water. So the moment it crosses this interface, if this is the normal to that interface, then it will not go straight down. No, it will either, in this case actually, it will bend towards the normal. It will become smaller. So you see, it was going like this in this part before. It has done what? It has bent. Okay? Good. Now, listen, listen. But if this guy were to be going, for example, in a straight downward direction, so the incident ray is going like this. Now, what will happen is this. The moment it crosses this interface, remember, this is not the solid surface. This is the interface between, say, air, for example, an optically less dense medium, to water, an optically denser medium than air. So by the time the ray of light, we are picking a ray of light now, goes from this air to water, what will happen is that since it is moving along the normal, directly perpendicular to that water, what will happen is that it's going to move, it's going to be, now this one will not bend, but it will still be refracted. Keep in mind, now, that's one thing students find hard to understand, that if I say a ray of light now is going down, perpendicular to the interface, then they will expect that it should bend, actually, like I showed here. But no, that's not the case. If this guy is acting, if the light ray is coming perpendicularly to the surface, but it's still refracted. Why? Because even though the light ray will not bend in its path, it will go directly down, undeviated. It will go undeviated. Okay? So meaning that the direction did not necessarily change. But the speed will change. Why? Because light travels faster in air than it travels in water. Because water is denser than air, right? And of course, more optically dense than air in this case. So what will happen is that what? As it goes down, the speed will reduce, and of course, the wavelength will also what? Reduce. Does that make sense? The wavelength will reduce, and the speed will also what? Reduce. So what that means is that you not travel too far inside the water. All right. That's why if you dive into a deep water body, what will happen is that you see that the light ray, the depth of the light will be reducing as you go down, right? Until you get to a point that you call, we have them in zones, okay? We have what we call the photic zones. The photic zone of that water will be the zone that enjoy a lot of light. Then as we go down, we have, so that zone there above the surface will be what? The pelagic zone, okay? Then here, midway, we have the mesopelagic. So in the mesopelagic zone, there is a little bit of darkness, okay? Why is there a little bit of darkness? Because the light is now reducing in its intensity. Does that make sense? As it goes down, of course, and as in its speed and in its wavelength. Does that make sense? Now, what happens? The moment you now get to what we call the abyssopelagic zone or abyssal plane around here, what will happen? You see pitch black. You see pitch black. Okay? Why? Because there is no light again. Do you understand now? All right. So, but notice, even though it is traveling normally downwards, it is still said to be refracted simply because the speed and wavelength will change due to the optical density of the water or any other medium that is denser than the former medium in which it was coming from. Does that make sense? All right. But we usually like to give the case where the light is actually traveling at an angle. All right. So listen now. So this light is traveling at an angle here. What will happen by the time it gets here is that it will not go in the direction of its motion again. It will, if this was the angle, remember, always draw the angle with what? Draw it to the normal, okay? From the normal to that angle of incidence. So this will be called the theta I. In this case, what? Angle of incidence. So this is this path that is supposed to continue in. But because of the optical density of this water in this case, or glass, is going to bend a little towards the normal. Do you see? It bends. So it got deviated. Its deviation happened, right? It got deviated from its normal course of direction of motion and got deviated a little towards the normal. So this is called the theta R, or angle of refraction. This is called what? Angle of refraction, or refraction angle. I hope this is clear. Good. Now, if light travels from an optically dense medium to an optically less dense medium, what happens? So we are going to see what happens based on the optical densities through which the guy moves. We want to examine that. Now, in the case where light, in this case, light is traveling from air to water. It is traveling from air to water. Air is optically less dense than water, meaning that water is optically more optically dense than air. What will happen is that the angle of refraction will be less than the angle of incidence. Does that make sense? I'll repeat that. When a light travels from what? From what? So this is the case. When the light travels from optically less dense to optically dense medium. But when the light travels from optically dense to optically less dense. Example of this one, less dense to dense, is air to water. In this case, it now travels from water to air. So for example, if I light a torch from inside water and to proceed outside, what will happen is that the angle of refraction will be greater than the angle of incidence. And I'm going to show you that. So look at what happens now. So let's say this is my interface between this water and air. So this is water here, this is water here, this is water here. If I send a ray of light at an angle like this, watch. If I send a ray of light at, let's say, an angle like this, what will be my angle of incidence? My angle of incidence, I'll draw my normal like this. Okay, so my angle of incidence is going to be here, so I call this theta I. Okay, now what will happen is this: because this is water is optically denser than air, so it's going from dense to less dense. Now what will happen is this: by the time it crosses this interface, what will happen is that it's going to deviate. Now this is the original path or direction that it was going, right? This was the original direction. What will happen? What will happen is that it's going to increase the direction. Do you notice now that it deviated? Let me show you well. It deviated. So this was the original path it was going before. But what happened? It deviated a little. So you are going to see that the theta R, the angle of refraction, is greater than the angle of incidence. This occurs when it is going from where? From dense medium to less dense medium. So that is refraction of light. All right. Now also keep in mind that some of these rays of light will be reflected. But I've already explained that when I was explaining polarization, because we can actually polarize light. I'll get to polarization, okay? I'll get to it. But keep in mind that we can polarize light by refraction and reflection. Now, let me now get to, let's now talk about what will now happen if I now increase this angle. I keep increasing this angle. I keep increasing. Before we get to that, let me explain an historical perspective of this whole thing that is happening. Remember that yesterday I told you that we use this guy reflection, okay, to create some stuff. I told you about sextants, right? I told you about sextants. I told you about periscope, yeah, and maybe even kaleidoscope. Okay, so periscope. We also use this. We use a phenomenon here to create a periscope. Now, before I entirely mentioned this. Okay, I told you sextants. We use it to view planetary, the angle of elevation of the sun and the star from the earth, and periscope for submarine. That submarine used before it will not get out of the water to view with a periscope an object that is above the obstacle. I hope you understand what I'm saying. Okay, so now my point is this: now that in the early, not early, about 140 AD, 140 AD. So a certain man, a certain astronomer actually was an astronomer. His name was Ptolemy. So some of you that do mathematics, you must have heard of the name Ptolemy before. Ptolemy's theorem that says that if you take the, for quadrilateral, for calculating cyclic quadrilateral, just search that, you will see Ptolemy's theorem for calculating cyclic quadrilateral. It's very simple, it's a very simple math. So this same guy, this same Ptolemy guy, he was my friend actually, but I'll tell you the story later. He was living beside, if you pass that side of your house, that small junction, that short, that junction that you see, that was where our house was before. Okay, all right. So my point is, this Ptolemy, this was what he did. He had already created a series of, he has tested the angle of incidence and angle of refraction of glass, of different types of glass, okay, and he has created a table for them, but he was unable to establish a particular relationship between them, okay. So as early as then, at that time, calculations, on refraction has, been ongoing, okay. Now, even scientists that came after him could not still establish a relationship between the angle of incidence and the angle of refraction, okay. It's now around the 16th century, about 1620, that a certain scientist known as Snell, he was also my friend, okay, we were also friends. This one was taller than me. Was taller than me, and me, I was fair. That okay, I'm dark skinned. Okay, he was fair. He was just my friend. Just believe that one. I believe. So now this guy was now the one in 1620 that was now able to create the standard relationship, the relationship between the sine of the angle of incidence and angle of refraction. What did he do? He found out that there was a particular set of ratio that they followed, that the sine of the angles of incidence and sine of angle of refraction, the ratio, that it was consistent for a given pair of medium. I'm going to give you his law so you understand what I just said now. So there are now two laws of refraction. Two laws of refraction. Two laws of refraction. So what is the first law of refraction? The first law says that the angle of incidence, before that, the incident ray, both incident and refracted ray, lie on the same plane. Do you know what that means? It looks like what? The law of reflection, right? Both the angle of incidence and reflection lie on the same plane. The same way here too. Lie on the angle, incident ray, and the line of incident ray and line of refracted ray, they lie on this same plane. And the plane is what? The interface between the media. So lie on the same plane, which is the interface between the media. So this is the first law. Now the second law of refraction now says that the ratio of the sine of angle of incidence to, that's the ratio of this, to the ratio to the sine of angle, sine of angle of refraction is constant for any given pair of medium. So what that means is this, that if I am comparing air to water, it means that every given pair I have, every given pair I have, the sine of angle of incidence for that pair to the sine of angle of refraction for that same pair will always be a constant number, a constant ratio. For example, if I use my first angle, my first angle of incidence. If I compare, for example, the sine of angle of incidence to sine of sine of theta I to sine of theta R, if I compare it for a particular air to water for a particular angle, and it gave me 1/2. Any other angle theta I that I take the sine of angle, it will be equal to 1, such that the sine of another theta R will be equal to 2. That is, we will always get this ratio 1 if, or I'm saying if it is ratio 1/2, it is 1/2 that I get for my theta I, which is for a particular medium to the second medium. I am going to get, by the time I solve it, I'm going to get that same that same ratio for that given pair of medium, regardless of how I change the angle of incidence. If I change the angle of incidence, the angle of refraction will change in such a way as to give rise to that ratio all the time. I don't know if you understand that. This is just for context, for example's sake, okay? If yes, I just hope you understand that. In case you don't understand, I'll link a video where I explained that, especially last year. I'm going to link the video, I don't know which year, but I'll link the video in the description, okay? But that's the law of Snell's law of refraction. So this way we write it. We say that this is just a symbol for it. So for any given pair of medium, in this case, A to W is given as sine I over this angle of incidence or theta I, okay, and sine of theta, sine of R rather, okay. So this ratio is also equal to the velocity of light, for example, in medium 1. In this medium, for example, air, in medium 1, which is air in our case, to the speed of light or velocity of light in medium 2. In this case, water. In our case, water. All right. So now listen, there's something now called absolute. Now you now know refraction. This is called refractive index. This is called the refractive index. Refractive index. Now there's something there's something that is now called the absolute refractive index. Now the absolute refractive index only occurs when the light is traveling from vacuum to a medium. So what does that mean? If we are taking the sine of angle of incidence in vacuum over sine of angle of incidence in the medium, or of refraction in the medium, this will be what you will notice, what will be observed is what? An absolute refractive index. If you are considering medium, you are considering velocity, it will be the velocity of light in vacuum, which is 3 millimeters per second, 300 millimeters per second. So that velocity in vacuum over the velocity of light in that medium. Does that make sense? Depending on which one you're talking about. Or wavelength of light. That's another formula for refractive index. So wavelength of light in that medium 1. In this case, for absolute refractive index, in vacuum, to the wavelength of light, the wavelength of light in medium. Excuse me. I felt a sharp pain. Okay. So that is that for this. Now, let's now talk about, so we are not talking about refractive index. Now, what will happen if I now keep changing this angle of incidence? What will happen? Okay. Now, here is what will happen. Let's say, for instance, I now take, let's say it was possible that I put, okay, good. Let's say I put glass here, from glass to air, for example. From glass to air. No, let me still use air water to air, that same thing that I cleaned here. So I'll use the same diagram, okay? So you understand, I'm from water to air. So I'm lighting, I'm going to on my torch from here, switch on my torch from this water to the outside. Does that make sense? So if I send my ray of light at this angle, you already know that what will happen is that it will be refracted at an angle greater than this angle of incidence via which I sent it. I hope that is clear. So it means that this theta r, you can see that it is greater than theta I. Does that make sense? Good. Now, what will happen if I continue to shift this my angle? Let's say I now increase my angle from here. I increase it to this place. See, I've now increased it. Let's now call this place theta 2, theta I2. What will happen? This my theta R, let's call this theta R1, will also increase again to what? Theta R2. I hope that is clear to us. What if I now increase this to an angle here that is very large? So this, let's now call this my new theta I3 now. My third angle of incidence. Now, what will happen to this guy is that a point will come as I'm increasing and increasing. Let's call that point this theta R3. At that point, you know, this thing will keep increasing, right? My angle of refraction will keep increasing more than my angle of incidence is increasing. So what will happen is that a point will come where this angle will increase and exactly be at the interface. That will exactly be at 90 degrees to the normal. So at that point where your theta R is equal to 90 degrees, that is exactly at the interface, at that angle of incidence, let me repeat that, at the angle of incidence, where your angle of refraction is exactly at the interface, or is exactly at 90 degrees to the normal, that angle of incidence is called critical angle. That angle of incidence is called what? The critical angle. So let me define it again now. The critical angle is a particular angle of incidence, not the angle of refraction. The critical angle we call critical angle, the angle we call critical angle is that angle of incidence that makes your angle of refraction equal to 90 degrees to the normal, or that makes your refracted ray lie exactly at the interface. Does that make sense? Good. Good. Now, what will now happen if I am stubborn and I decide to still increase this guy? I said go for that. Now, you may think that it will go back. No, it will not go back. What will happen is that the moment that I increase this guy, remember that my critical angle for my example here is theta I3, right? My third angle of incidence is this my critical angle. What will happen if I now increase is greater than theta I3? The moment I go greater than theta I3, what will happen is that total TIR, that's what we call it, okay? We call it TIR, that is total internal reflection. Total internal reflection. So TIR for short. Total internal reflection. Now I'm going to tell you one of the consequences of total internal reflection in real life. Total internal reflection. So do you now understand now? So what is now total internal reflection? Total internal reflection occurs when the angle of incidence, when does it occur first? Total internal reflection occurs when the angle of incidence is greater than the critical angle. The critical angle is given as theta C, that's what we call it. Critical angle. This is the angle where your angle of refraction is exactly lying on the plane or is exactly equal to 90 degrees, right? That's the angle of incidence where your refracted angle was equal to 90 degrees. Your critical angle, note, is your angle of incidence, not this angle here. Is that angle of incidence that makes your angle of refraction equal to 90 degrees. But anything greater than the critical angle, you get what? A total internal reflection. Now, what does that mean? It means that this ray will continue to increase and come and be reflecting itself. That's why we call it total internal reflection. Total what? Internal reflection. Why? Because it's now reflecting back in the medium that we're propagating from. Does that make sense now? Is that God bless you? All right. All right. Should we continue? Yes, let's continue. Now, what is the physical phenomenon or real life phenomenon that we can explain with total internal reflection? Now, you must have heard about what is called mirage, right? Okay. Now, what is mirage? And it's not marriage, it's mirage. Okay, here's the transcription. Mirage. Mirage. Okay. Now listen, what is mirage? Mirage is, if you have ever traveled on a on a hot day, now on a tarred road, what will happen is that if you look far ahead of you on that asphalt, that your tarred road, the road ahead of you will look as if will look like there is a pool of water in front there, but by the time you get there, you will not meet any pool of water. Now that is mirage. Now how does that occur? Now what happens is that if this is the surface of that asphalt, because it's a hot sunny day, the air molecules that are closest to the surface there, they are hot. Now what is the major characteristic of hot air? It will be less dense. The air molecules that are on this surface here, they are cooler than the one that are closest to the surface here. Let me explain that again. The air molecules closest to the surface, because it's a hot day. Because this is black, asphalt is black. I mean, the asphalt we use on our road, on the tarred road, is black, right? And you know black bodies radiate a lot, right? They absorb all the light. I told you black is not a color, right? It is simply the absence of ROIC B, right? Because it absorbs all of ROYGBIV. If you don't understand what I mean, just tell me in the comment section. I'll make another video for you on that, explaining that alone. So now, since that's the case, then it means this air molecules above this surface is going to be very hot. But the air molecule that is just above that one will be cooler than this air molecule, right? So meaning that the ray of light, so this is your father's car, for example, or your car, or your own car, for example. So this is your own car, for example, traveling on this road. Now, so what will happen is this, that the ray of light coming here is going to pass through the air. This one, remember, this is cool air. This is cool air, and this is hot air. Now, there's an interface between them. So this is the surface of hot air. This is the interface between cool air and hot air. Your car is far away, okay? Now, what will happen is that this air here is denser than this one here is less dense. I repeat, the hot air here is less dense than the cool air. So for that reason, air will now be, that light ray, incident ray, will now be moving between what? So let's say it was this direction. It will now be moving between what? Let me bring it here. It will now be moving between what? This light that is coming from the sun here is going to be moving between a dense medium to a less dense medium. And what happens at that time? In that instance, what happens is there's going to be what? Refraction. So since there is refraction, because there's now optical density between the two air interfaces, between the two air spaces or air molecule, air regions, there is now different optical density because one is now dense air, the other is now less dense. What will happen is that reflection will occur. So as your car moves closer, at the point where your car is far away from it, the ray of light here would have been greater than critical angle. So for that reason, there is total internal reflection happen to your eyes happening at your eye level here. Are you getting me now? It's happening at your eye level. So because of that, now why is it happening? What are you seeing as water? What you are seeing is actually the cloud of water that light passed through. The cloud of water you are seeing here that the light passed through is the one that is reflecting on yourself on your eyes inside the car here. So and that's because you are still far away. So your angle there, your eye level there is still making the angle of incidence of this one to be greater than the critical angle. I don't know if you understand what I'm saying. So if that be the case, you are now there is now an incidence of what? Total internal reflection. So by the time you now get very close to this thing, you would have been at an angle that the incidence angle would have become almost over your head. Do you understand? It's now closing into the normal. So for that reason, the angle of the total internal reflection stops and you can no longer see the pool of water. I hope I did justice to that. If you didn't understand, just rewind a little bit and watch again. You'll see that you'll understand what I just said. All right. Now, what are the use of total internal reflection? One of the uses is periscope also. Okay, the periscope is what these guys on the sea, they use it to use it for navigation, yeah, for navigation. So in submarines, I said they use it to see above obstacles. Okay, so but we're not getting to the use today because I also in this video want to show you some of this I showed you yesterday in reflection. That's about images formed, okay, image formation. But God will help us, because there's something I remember now that I'm supposed to also talk about. Now, another thing about refractive index is this. Now, let me also tell you a consequence of refraction. If you place something inside water, for example, if you place something at the bottom of water, let's say this is water here. If you place something here, let's say you place a box here. Do you remember that if you look at this thing at any angle anyway, you see that it will look like this bottom. In fact, if you look directly at the bottom of your water, you see that it's closer, it will look as if it's closer to your eyes, right? Yes. So the same thing here, this box will be appearing somewhere here. It's as if it has shifted. So this depth here, from here to here, is called the real depth of your distance. So this is where the real depth of your box. But from here to here is the depth you are seeing. Okay? So we call this the apparent depth. So another formula for calculating refractive index is the real depth over your apparent depth. That's another formula for what? Refractive index. Real depth over apparent depth. Now if you notice, if you want to calculate, you notice that the real depth is from here to here. Okay? So if that is the case, that the depth has shortened, then it means that the depth you see is going to what? Your real depth minus your apparent depth. Does that make sense? The depth difference, rather, the deviation, did I say depth? I'm sorry. Deviation, rather, is going to what? Your real depth. This will be the deviation. Because this plus this will make the real depth. But the deviation is going to what? Your real depth minus your apparent depth. The moment you bring this into context, from here, if this is equation 1, I will call this equation 2, for example, then A from equation 1 can become R over N. Does that make sense? So what that means is that the deviation is equal to R or depth difference, okay? R minus, so if you substitute, put this guy into this equation 2. So it becomes R minus, A is R over N now, R over N. So by the time you factorize R out, D becomes R into bracket. R is coming here between 1 and minus 1 over N. So let's call this equation 3. So this is another formula for calculating the deviation. Okay, so in the case where you are giving the deviation and the real depth, you can use this formula. So now we know total entire reflection, we know real depth and apparent depth. Now, let's talk about then reflection also, refraction rather, is also what makes sound waves. I've explained that before. It's what makes it to travel faster in the night than it does in the day. It travels, you see that you can hear sounds louder in the night than in the day, right? It's due to refraction. All right. Now, listen. Let me now give you. How about in a prison? In a prison, let's talk about the reflection in a prison. So, for example, if I have a prison, now the designation of refractive index of a prison, that's what we want to talk about, so that you know what you write on top. Refractive index of a prison, of prisons. Now, with prisons, they have a special design. We show the triangular part, this triangular portion, because that's where our refraction is occurring. So now there is also a specific design for them. They are designed in such a way as that they have what is called a refracting angle. So most of these prisons, they are designed to have 60 by 60 by 60 degrees triangle, or some have 90 by 45 degrees triangle. So I'm going to be using one that is designed to have an equilateral, to be an equilateral triangle, having 60 by 60 by 60. So this place is called the refractive angle A. Is that clear? It's called the refractive angle. Now, if a ray of light, now this one should not confuse you, so just follow me. Let me make the triangle bigger so that it will be clearer to people. I don't want it to confuse you at all. Just like I explained that, because I might be deriving other equations here too. Now, this is my refractive angle, not refractive, or refracting angle. Now, if my ray of light is incident at an angle like this or like this, we like to use from here, for example. So my ray of light is incident like this, it's comes and touches this surface like this. So it's going from air to what? To glass or prism. Now, how do I check my angle of refraction? I will first erect my normal. My normal must be perpendicular to this surface. So I draw my normal like this. Does that make sense? Good. Now what will happen? This thing will deviate. So on deviation, it can deviate to, maybe let's use a straight line, because this is its original path, right? It's going like this, it's supposed to continue like this. Does that make sense? It's supposed to continue like this. Okay. So we will now say this here is the deviation. So let's call this first deviation. But this angle that it bends to, instead of continuing, this place is the angle of incidence, the angle between the normal. Don't let it confuse you. This is the normal. It's always perpendicular to the surface. So if this is my angle of incidence, this will be if this is my angle of incidence, yes, we'll read it to normal. My angle of refraction, instead of continuing like this, instead of my ray going like that, because this one is optically denser, it will shift away a little. It will bend towards the what? The normal. Always remember that it is bending towards the normal. Okay? Because this is supposed to be the size of the angle of the refraction. But the angle in which, since this is incidence, if angle of incidence is the same as the angle at which it enters this angle, my prism, it should be the same. This entire place should be what we have, but it is bending towards the normal. Exactly, it's bending towards the normal, so we say it has deviated. So the angle of refraction, we also read it to the normal. Remember, this will be the R1, first angle of refraction. Now this guy is also going to come out here at an angle. By the time he strikes this place, it's still come out at an angle, isn't it? So since it's coming out at an angle, then we can also trace this angle at which it's coming out backwards into the prism, and you notice that it has deviated a second time. Let's call this place D2. I hope you understand what I'm saying. So this angle here, we also erect our normal to be able to calculate that angle. This is our normal. So this angle here will be called the angle of emergence. So this ray here is called the emergent ray. Emergent ray. And this one is your incident ray. Is that clear? Then this one is your what? Your refracted ray. Please don't forget, refracted ray. Let me not write it. You just label it in the way you understand. I don't want it to scatter what I'm doing here. So this one is the deviation 2. Why? Because if you read, so our ray of light went like this, and out like this. If we had come like this too, it would have gone like this, deviated towards the normal like this, and again deviated, gone out like this. Okay? Good. Now listen. Let's call this, now since it's going like this will be our second refraction. So let's call it R2, because this is the shifting towards the normal, R2. Is that clear? Good. Now, so the first deviation experience, deviation 1, is going to be what? Because it's going to be, this entire place is the same as our angle of incidence. So deviation 1 is going to be what? Angle of incidence minus R. Does that make sense? So incidence minus R1. I don't know if you understand that. Look at it, this entire place. Just use vertically opposite angles are equal, you get it. Does that make sense? So you now subtract this R from incidence, you get your deviation 1. Now your deviation 2 also will be equal to what? Emergent ray minus what? Angle of emergence minus refracted angle of second refraction. How this is clear? Good. Now, what will now happen? So if you want to calculate the total deviation that light experienced, this is what we mean by total deviation. See, if you calculate it, this total angle, this is the total deviation is from here, because this is where we started from, right? So this is total deviation, D. Is it clear? So how do you get the total deviation? The total deviation will be equal to D1 plus D2. I hope that makes sense. And remember that D1 is already I minus R1 plus E minus R2. So this will be the formula for total deviation. But now listen. If there's now for minimum deviation to occur, the least deviation, minimum deviation, that is for the deviation away from that normal is original path of motion. For the light to experience minimum deviation, that is the smallest deviation, it means that the I must be equal to the angle of incidence must be equal to the angle of emergence. So if angle of incidence is equal to angle of emergence, it therefore means that R1 will also be equal to what? R2. So in such a case, deviation 1 will be equal to I minus R. Deviation 2 will also be what? Deviation 1 and deviation 2 will be equal. So it means that deviation 2 will also be emergence minus R, because R will be equal to R. Does that make sense? So in that case, since I is equal to E, then total deviation D is equal to what? So now, in this case, what? Minimum deviation. Total minimum deviation of what? 2 into bracket I minus R. Why? Because it will be deviation 1 plus deviation 2, which is equal to this and this, and this is equal to this. Then it will be 2 times of this minus this. That is IO, angle of incidence, minus angle of refraction. I hope that is clear. Now, if this is clear to you, let me generate an equation for you. Now watch. You already know that this is now our angle of incidence. Now, there is something you must know, that for an equilateral triangle like this, that has 60 by 60 by 60, for equilateral triangle now, for equitriangle, the minimum at minimum deviation, at D minimum, for an equilateral triangle, at D minimum, the angle of refraction is always equal to half of the refracting angle. That was what was experimentally discovered. That one was discovered experimentally. That for a prism that is designed at 60 by 60 by 60, for such a prism, at minimum deviation, R will be equal to half of A. Does that make sense to you? R will be equal to what? Half of A. Now, if that is the case, therefore, then it means that if we make this, if we bring this into this equation, then our D minimum will now become, no, since we already have an expression for this, we can make R subject of formula here. For example, I want to give you another expression for let's rewrite this expression first in terms of this. D minimum becomes 2 into bracket I. I'm trying to generate an equation, okay? I minus, what is my R here? R is already A over 2. I hope this makes sense. Now, if this be the case, then I'm trying to generate an equation here. I can't remember the equation, okay? That's why I'm not remembering it well. Sine of angle of incidence. So what will be my angle of incidence here? According to this equation, what will be my angle of incidence? My angle of incidence here is going to be equal to D over 2 is equal to I plus I minus R. So that I will be equal to D minimum. This is D minimum. I just divided both sides by 2, okay? See, divide both sides by 2 over 2. You have this. Does that make sense? So by the time you do that, I will now be equal to D minimum over 2 minus R. Plus R. But remember that I said R is now what? A over 2. I've gotten my answer. R is now A over 2. So from here, so just eyeball this. I don't think this is useful. So I will now become D minimum over 2 plus A over 2. What does this mean? I becomes what? Minimum deviation plus refracting angle over 2. If we now input this into our formula of refractive index, which we said was sine of angle of incidence over sine of angle of refraction, therefore becomes the sine of, what is incident angle? Incident angle there is what? D minimum plus A over 2 all over the sine of R. Sine R, what is R? A over 2. I hope this makes sense to you. Now we've gotten here. So you can use all these formulas, okay? See, I want you to know how these formulas are generated. They are not hard at all, okay? I now want you to also know how to form images. Okay, this is what I'll do. The video is already, let me see how long it is. The video is already 53 long, okay, 53 minutes. Let's see if we can do 1 hour so that we will cover image generation. I will do only 1 or 2, just like I did yesterday. Then you'll be able to do the rest, I promise you. Right. Now, refraction, just like reflection, reflection occurs with mirrors, but refraction occurs with lenses. I repeat, reflection occurs with what? Mirrors. Refractions occur with what? Lenses. So we want to see refraction in what? Lenses. These lenses. Now, there are different types of lenses. Just like we had them, we have concave lens and convex lens. Concave lens. Now this concave lens is also called a diverging lens, while this convex lens is called a converging lens. So don't let it confuse you. I probably told you yesterday that concave lens is concave mirror is converging mirror. Concave mirror is converging mirror. Convex mirror is diverging mirror. But concave lens is diverging lens. Convex lens is converging lens. Is that clear? Good. But there are different types of concaves too. So a concave, we can have, now watch, we have a shape like this. This is a convex, this convex shape, okay? So this is biconvex because it's convex on both sides. Is that clear? If I now have a plane and a convex, this will be called a plano-convex. This is what? Plano-convex. This one biconvex. This one plano-convex. What if I now have something like this? This one will now be called a convex meniscus. Okay? What of concave? The same way. This is going to be called biconcave. Then this one will be called a plane and a concave, right? That will be plano-concave. Then we now have something like this. Concave meniscus will now look something like concave meniscus. That will be something like this. This concave meniscus, like this. So this will be concave meniscus, something like this. Okay. Now, so then let's now talk about images formed. So just like we had yesterday, we have principal focus, we have, but the difference is this. For in this case, you know that one ray of light will bounce off for mirror. Here to pass through. Don't forget, for lenses, it's what? Pass through. So let's discuss some rules that we need. First, know the parts. Let me show you the parts. These are the parts. This one is called the principal axis. Put your mirror, your lens in the center like this. Put your mirror in the center, at the center. Okay? Even though my own is not falling in the center perfectly. This will be called the pole of the lens. Now, from here to here, to a particular point here, we'll call it the focus. So there's focus here, there's focus here. So there are 2 points that we'll call, so there are two foci. Okay, foci. I wanted to show you something yesterday. Now, the power of a lens. Power of a lens. Not yesterday rather. I remember something. The power of a lens is given by the formula P equal to 1 over the focus. 1 over focal length. Where P is power. P is what? Power. And F is focal length. And the power of a lens is measured in diopters. Power of a lens is measured in what? Diopters. Right, let's go on. Are you tired? No. Because I'm not tired. Are you tired? You can't be tired. Amen? Amen. So now, from pole to F, the distance apart again will be 2F. We call it 2F. So from here, we'll bring that distance here to we'll get what? 2F. So there's 2F1, there's so if these are fronts, for example, if the observer's eye is here, the object will be here. Does that make sense now? The object will be here. If the observer's eye is here, the object to be on this side. Is that clear? So that's that. So we can call this f prime and 2f prime because I want to use this as the side where I have my object. Now watch, please watch. So the rules, a ray of light that you draw to be parallel to this, to be parallel to the principal axis. Just like yesterday. When it's being reflected, it will converge. Remember, this is a convex lens, so it will converge. Does that make sense? Good. So it will converge. But when it's being converged, remember, it's going directly. It's not reflection. It will refract. What that means is that when it gets to the center of the mirror here, instead of continuing in its path of motion, it will refract. Do you know how to use? It will refract. Now, when you are refracting it, you refract it towards the focus. Focus. This is straight line. All right. So what happens is that when you draw a ray of light to be parallel to this principal axis, by the time it's being refracted, it will be refracted towards the focus. If you now draw a ray of light to pass through your focus, for example, let's say from a point, you draw it to pass through your focus. Hey, Jesus Christ. Pass through your focus. Hey, Jesus Christ. Let's just assume that it's going through the focus. So let's increase the size of our mirror, of our lens. Let's increase the size. These are our lens now. So you see that this ray of light is stopping here. At this center, instead of continue towards its path, no, it will refract. What will it do? It will bend. This is where it will bend. It will bend in a direction that is parallel to the principal axis. You see? Parallel, parallel. You see that? So because of the principle of reversibility of light. Alright. So a ray of light that was coming like this, when it touches the lens, it will be refracted towards a direction that is what? Parallel to the principal axis. That is provided if it passed through the focus. But if it's parallel to the principal axis, when you draw the ray of light, let it converge towards the focus on the other end. Then the last rule that you need to draw your image for image formation is that if you draw a ray of light to pass through the center of your mirror, of your lens, it should go through undeviated. So like this, it means that it is passing through the normal of that lens. So it should go through undeviated. Let me draw just one for you. You can draw the rest. In case you did not understand, you were unable to draw the rays, now put in the comment section. I'll now do image formation alone. I'm going to show you, and I'll show you all the images you can form. It's very, very simple. But as a good student who has been listening to me so far and has been paying attention, rapt attention, you should be able to do the rest when you watch me do this. So pay rapt attention like I've been doing as a good student. God bless you, and you'll get this. Now watch. Let's say, for example, I now put my image at away from 12. If I call this place my 12, so let's say my object rather than sorry, not image. I place my object, for example, here. And my mirror, my lens is going to be here. Let's call this point F, my focus, my 12. So this is the pole. So from here to here, that will be like here. Okay. Now, when you are drawing your own, the mistake students make is sometimes they make their lens too thick. If your lens is too thick or unequally thick, you might get wrong answer. In that video, I've showed you how to draw it. What you just do is create a point. This is from 12. From 12, just create an arc. Pick another 12, equidistant. Create another arc with your pencil, then clean, and you get a slim, quite slim. What I mean by it should not be too thick is you use something that looks like this is too thick for your lens, okay, to affect what you get. So here, I'll have 12 at this point, 12 prime. Now watch. If I draw my ray of light to pass to be perpendicular to this guy, By the time it's is converging, what will happen to pass through the focus? If I now draw my ray to pass through the focus from the start here, remember, I want to form the image. If I draw my ray to pass through the focus like this, by the time it gets to the center of the mirror, of the lens here, what will happen? It will refract in a direction that is what? Perpendicular, parallel to the guide, to the principal axis. Okay? This is my second ray. So wherever they meet, I told you yesterday, is where you form the place that you started your ray from. I started from this edge, it means that the head will form here. So you now join the body to the other place, okay? Join the body. So what do you see with this? You will notice, let's write the characteristics of the image form. This is on image formation, okay? Image formation. So write it as a topic, please, subtopic. I'm sorry I'm not organizing as well because of tiredness. But please just try. Now watch. You see the size of this guy. What happened? Look at the size. What happened? It has become smaller. So image is what? Diminished. Image is diminished. What else? You will notice that the distance, that the image object distance is greater than image distance. Look, because what's the position of that one? The position of image here is what? Between what? Between f prime and 2f prime. But remember, what you put here, you put your image is at very far away from 2f. Do you understand now? So that's very important for you to note. Another thing is this: your object is standing, your image is going upside down. So what does that mean? Which word did I use for yesterday? As what? Inverted. God bless you. And I've told you, when you hear inverted, when an image is inverted, the image is what? Real. So we have real and inverted. We have what? Real and what? Inverted. We have real and what? Inverted. So that is that for that. Exactly. So you can try it on your own. Provided you draw it according to the rules I give you, you get to see, you get correct answers. But I've told you yesterday, the most important rules, the most important characteristics of this image are these: diminish the size, the position, and whether it is real or virtual. If it is erect, it will be virtual. So we have virtual and erect, then we have real and inverted. Does that make sense? Good. Now, then of course you have the lens formula, just like your mirror formula. That's going to be what? 1 over f is equal to 1 over v plus 1 over u. Do you understand? So that's what you have. So so that's it. Sorry, minus, sorry. Is it plus or minus? Yes. 1 over v minus 1 over v. Sorry, am I confused? Please let me quickly search for it. I'm sorry for confusing you. My head is already fuzzy. It's correct, okay? 1 over f equals to 1 over v plus 1 over u. Please do well to subscribe to this channel. Tell me if there's any other question I'm going to answer. Any other topic in physics or chemistry or mathematics I want me to release video on, I will release them. Then I told you, I promise you this weekend I will release that alkaline video. I'll shoot it again. Okay? But I told you the reason why I could not shoot that video. God bless you. Do well to subscribe to the channel.